Now it's time to investigate one of the most important properties of elementary particles. One that literally shapes the atoms of each element in the periodic table. Jeeves, please continue.
We have just discussed how Schrödinger's equation shows us how to accurately describe fundamental particles with a wave function. Now let's examine why two electrons together reveal a feature of quantum mechanics totally unlike anything in the large-scale world we inhabit. In a classical setting, even if two things are identical, they are still individuals. As long as we keep track of them carefully, we can treat them separately and label them A and B, or X and Y, or 1 and 2. But consider what is different about a two-electron system. Whether in an atom or in a box, it doesn't matter. Since the two electrons are consistently phasing in and out of existence, and since they are absolutely identical, it is impossible to keep track of specific individuals. Because of this, we must use a combined wave function to describe the pair rather than using two individual wave functions. This new two-particle wave function will have two parts to it, and those parts will either add or subtract. Physicists would say this makes the wave function either symmetric or antisymmetric. And it turns out that only the antisymmetric function works for the electrons, and quarks, and protons, and neutrons. Let's let this red wave represent the first part of the combined wave function, and this green wave represent the negative of the second part. If the electrons are in the same state, these two waves will be a mirror image of one another. As one goes up, the other goes down in perfect synchrony. So when we combine them, we get no wave at all. And since the wave is a map of electrons existing at that point, no wave means no electrons. So clearly, two electrons can never be in the same state because that causes their combined wave function to disappear. Now the only components making up the dynamical state in the atom is the shell it occupies, and another property that electrons have called spin. You can think of electrons as little spinning tops if that helps. And these electron tops can spin in only two ways: upright or upside down, which can make them distinguishable. So the end result is that two and only two electrons can occupy each shell in an atom, one with spin up and the other with spin down. Other electrons in the atom must occupy higher and higher shells. This is called the Pauli exclusion principle, first espoused by Wolfgang Pauli. Without this exclusion, all electrons would occupy the lowest energy state, and atoms would behave very differently, and the universe would be a very different place. The fact is that the property called spin is quantized as well. No big surprise. And all the particles fall into one of two different families because of this. Those particles that have spin equal to 1/2, or 3/2, or 5/2, and so on, form the family called fermions. The name comes from Enrique Fermion, who along with Paul Dirac developed the statistical methods of dealing with them. Fermions are said to have half-integral spin. And as indicated above, Electrons, quarks, protons, neutrons are all in this family. The other family of particles have spin equal to 0, 1, 2, 3, and so on. They are called bosons, after Satyendra Bose, who along with Einstein developed the statistics for dealing with this family. Unlike fermions, which must obey the Pauli exclusion principle, bosons do not. Groups of multiple bosons will all gather in the lowest available energy state. Photons, gluons, gravitons all fall into this family. If bosons had to obey the exclusion principle, many modern marvels could not exist. Like lasers, which require that huge numbers of photons be in the same state at the same time, and again, the universe would be a very different place.